Let's start our three little sessions. I've got a little segment on standard errors, and then I'll be talking about interpreting coefficients. And then finally, we'll finish up talking about dummy variables and the equivalent ANOVA runs. So first off, standard errors. This is not something that I have had in past classes, but it occurs to me it might be useful to kind of consolidate what I have to say about standard errors in one little segment here. So, I've been talking about how important the coefficients are, right? The goal was to have unbiased estimates of causal effects from regression coefficients. And that's certainly the most important goal. But I'm fond of saying that standard errors are almost as important as regression coefficients are. And that's because they have a lot of information to tell you. So first off, obviously, they show how confident you should be about the size of your estimated effect, right? That's the confidence interval. Something that you learned last quarter. Obviously, also, you want that confidence interval to be as small as possible. So the question, how to make standard errors as small as possible. Third, and this is less obvious, is that you can use standard errors to diagnose multicollinearity problems. That's when you've got a bunch of independent variables and they're all highly correlated. And in fact, they're so highly correlated that you start to, the regression starts to blow up in the sense that its standard errors start getting bigger and bigger and bigger. You don't want that, but also on the other side, you often want a lot of control variables to handle potential omitted variable bias. So how do you strike this balance between too many and too few? My rule of thumb is to add in these correlates up to the point where multicollinearity problems start to show up, right? So standard errors are useful in pointing to where that is. And then finally, and this is something we'll talk about in the very last week of class, you can use standard errors to help understand the amount of statistical power that you have. What is your ability with your sample to estimate a size, an effect size of some value X, right? Oftentimes, you'll want to be confident, but obviously you want to be able to detect an effect size as small as possible. And if your sample size doesn't enable you to detect an effect size of, let's say, less than half a standard deviation, which is a huge effect size, then it's not a very useful sample. So you should be shopping around for other samples, larger samples. So the standard errors can be used to determine that. So that's my agenda here. And let's start out with the first item on the agenda. Standard errors show how confident you should be about the size of your estimated effect. Let's say you have an experiment and you're estimating an effect that is in standard deviation units, right? So you really want to know how big is the difference between the treatment group and the control group, and we're expressing that in standardized units. And let's say that you first estimate an impact of 0.2 standard deviations with a standard error of 0.05. Okay, so your estimate then is 0.2 standard deviations right here. And you want to know how confident you are that it's around 0.2. And that's what the standard error tells you. Roughly speaking, 2 times the standard error on either side of the coefficient. is the confidence interval. And in this case, because we chose 2, this is the 95% confidence interval. Okay, so in this case, we've got 0.2 minus twice 0.05. Where we go down to about 0.1 or so. 0.2 plus twice 0.05, we go up to 0.3. So this is the 95% confidence interval. Associated with that estimated impact and that standard error. Now, I didn't do a very good job of talking about how to think about statistical significance before. It's easier to do with confidence intervals. If you have a 95% confidence interval, the idea is that if you were to draw, let's say the sample size is 250, if you were to draw 100 more samples of 250 from similar populations, ran this regression, you'd expect that the difference between the treatment and control group would be between 0.1 and 0.3, 95 times out of 100. Okay, so that's pretty good in terms of the traditional kind of hypothesis testing, which is whether the confidence interval includes 0. How confident can you be that the next time you ran the experiment, you wouldn't get an estimate of 0? In this particular case, you're pretty confident because that confidence interval is a ways away from 0. Let's consider this second situation, identical coefficient, 0.2 standard deviations, but now we've got a standard error of 0.15. All right, so now we're starting at the same spot, but now we go down twice 0.15 or 0.3 to minus 0.1. And the upper end of the confidence interval is 0.2 plus twice 0.15, or all the way up to 0.50. Okay, so that makes us uncomfortable. It makes us uncomfortable in particular if we want to know how confident we are that the estimated effect is not 0, because 0 is included in the confidence interval. We're not very confident at all if that's the case. I might note that 0 isn't the only hypothesis that you might want to test against. Let's say you're doing a replication of some sort of experiment. And the literature seems to show pretty big impacts. Let's say 0.4 standard deviations from this experiment. A lot of people have done it. The average effect size is 0.4. So one question, instead of how confident you are the effect size isn't 0, you could ask, in this case, how confident you are the effect size isn't 0.4, right? And in this case, if you've got a big enough sample to get a 0.05 standard error, your confidence interval doesn't include 0.4. It's just like 0. It's that far away from where your confidence interval is. So you can be quite confident that the effect size from your particular sample, well, from the population that represents your sample, isn't as high as 0.4, right? So in both cases, it helps to be precise, and precision is having a small confidence interval. One question, this often happens. Let's say you have the smaller sample size, get the 0.2 estimated effect size, standard error 0.15. What's your best guess of what the impact of that treatment is. A lot of people would say 0. You can't reject that it's different from 0, therefore your best guess is that it's 0. But that's not right. Your best guess is that the effect size is 0.2. That's the estimated effect size, right? You just can't be that confident that it's 0.2, but you're equally unsure about whether it's as low as minus 0.1 or as high as 0.5, right? So the best guess is 0.2. That's important because yours may not be the only study out there estimating this impact. There was a big literature early on looking at the effect of class size on student achievement. And a lot of the early studies had relatively small samples. So they were getting estimates of class size, let's say a reduction of 3 students on average was associated, let's say it was with a 0.2 standard deviation increase in achievement. With a small study with a standard error of 0.15, you can't be that confident that the 0.2 is real. You don't know whether it's, it could well be 0. But suppose you had 10 of those studies, or suppose you had 20 of those studies, and pooled them all together. Individually, every one of them, if they were all estimating a 0.20 coefficient and a 0.15 standard error, individually, none of them could reject the hypothesis, the null hypothesis that there's no impact. But you can combine studies in meta-analyses which pool together estimated coefficients from the literature and are powered by the total sample size. Not just the sample size of one individual study. So as it turns out, there was a famous meta-analysis that Larry Hedges did in the late 1980s, I think, where he looked at the literature and gathered together all the estimates of class size. The kind of conventional wisdom was that there wasn't any relationship because all these individual studies were showing no significant relationship. But then he conducted a meta-analysis, and simplistically, he came up with the same 0.2 estimate. But because he was able to pool together the power from all the individual studies, he got a much smaller standard error on his pooled estimate of the effect of class size on achievement. And that really was a revelation to a lot of people. And so the result was that you can't simply discard an insignificant estimate because you've got too large a set of standard errors, because you can think of them with this 0.2 as being your best guess, and someone may come along and do a meta-analysis. Any questions? I've got Paul standing by to channel questions from the class.
I don't have questions, but we have a student with us
who
may or may not say. I'm not sure if he.
Okay, well, yeah, it was completely voluntary, and they should be encouraged if they have other important things to do in this day to do those other things. But if they want to stay, that's fine. If they want to ask questions, that's fine too.
Okay.
Okay. All right. So that's how to think about the use of standard errors in showing how confident you are that the effect you're estimating is real. It should be obvious that there's every advantage to having a smaller rather than larger standard error. And that raises the second question, how to make standard errors as small as possible. And we'll talk about two ways here. One is increase sample size. Because standard errors fall with the square root of sample size increases. So if I quadruple the size of the sample, I cut my standard errors in half. All right, that's a just a straight up statistical fact, and pretty intuitive, right? The larger sample you have, the more precisely you're going to be estimating any of the coefficients in your regression. Second trick is to include covariates that are highly correlated with the dependent variable. In other words, increase the R square and we'll talk in a minute about exactly how that works. But let's just first do A. Is it the case that standard errors vary with the sample size? So let me pause for a moment and walk you through some output to show you that.
Okay.
Okay, so we are looking at some output to try to illustrate that standard errors change with sample size change. This is a class data set. You can see some familiar variables here. We're taking test scores. Our basic equation is to try to look at impacts of some fairly randomly designed variable, randomly assigned variable on 5th grade test scores. Okay, if you think about the ECLSK, it's not an experimental data set, but if you just ask what variable in the data set is fairly randomly assigned and has a 50-50 split to it, child gender qualifies. It's a Nice variable. We're not at all interested in the effect of child gender, but we're very interested in the standard error on child gender. So we're going to be looking at test scores in the spring of 5th grade. Our covariate in the second half of our look is going to be spring of 1st grade and spring of kindergarten test scores. These are reading scores. So first, take a look at Paul's attempt to standardize these scores. We're standardizing within grade. And then here's the dummy variable for whether female. As you can see, he successfully calculated for these a mean 0 and standard deviation of 1. These are extremely small numbers. And then the female-male split in the sample is about 49:51. So we've got standardized variables. Now, to make things simpler, we're going to whittle down the sample so that every observation has valid data across all the test scores that we want to be looking at eventually. And when we do that, we end up with a sample size of about 9,000. The study began in kindergarten, and by 5th grade, there was considerable sample attrition. So we've got 9,000, almost, well, you can see if you standardize on the entire sample, you're left with, in 6th grade, a sample with test score averages that are about 1/10 of a standard deviation above the mean, right? So you tended to get keep the higher achievers and lose the lower achievers. But that won't affect our purposes here. We still have about a 50-50 split for gender. Just to describe the data a bit, here are correlations among the reading scores. Kindergarten, 1st grade, and 5th grade. Not surprisingly, they're very high. So let's start with a bivariate regression, where we've got 5th grade reading scores as the dependent variable and child gender as the independent variable. Okay, and you can see standard error is pretty small, 0.020, but the whole point here is to ask whether that standard error changes with a change in the sample size. All right, so we can't quadruple the sample size. We're kind of stuck with what the ECLSK sample size is. But we can go the other way, and we can randomly throw out 3/4 of the 9,600 observations to get a much smaller number of observations, 1/4 the size. And if you think about what happens, it's kind of the reverse. If you quadruple sample size, standard errors drop by half. If you go the other way and take out 3/4 of the sample, so you have only 1/4 of the original sample, then you ought to get an increase in the standard error that's equal to the square root of the 3/4 drop. So if quadrupling drops the standard error in half, then taking only a random 1/4 of the sample ought to double the standard error. So let's do that. Paul has generated a variable that enables him to look at a random 25% of the sample. Paul, you want to say anything about that function in Stata?
Yeah, and we can cover this more in lab, but our uniform is short for random uniform. It creates a random number between, I think, 0 and 1, but in a uniform way, so that if you were to create a histogram out of the random number you generate, it should sort of look like a big rectangular box, which would be different from like our normal, which would draw like a random number from a normal distribution. But anyway, because these are uniformly distributed, it's easier to capture what 1/4 would be if I take all the random numbers that are less than or equal to 0.25. It basically takes that rectangle and you take 1/4 of that rectangle on the left side.
Perfect, thank you. Okay, so we do that and we end up with 25% of the observations, 2,278. So let's see what happens when we repeat our original regression. We saw this before, our 9,000 observations, standard error 0.02. Now we condition on the first quarter of this uniform variable. So we get down to our 2,278. Standard errors should approximately double. And voila, they almost exactly do that from 0.02 to 0.04. So sample size matters a lot for standard errors, and the bigger the standard errors, the better. So why don't you pause again, Paul, and I'll go back to the board.
Okay. You just said bigger the standard error, the better. You mean smaller the standard error and larger the sample size, the better, right?
Yes. Okay. Turn on record again.
We were on recording.
Okay.
I just added that. So
Okay,
I'll
good.
pause record.
Yeah, pause it now.
Okay.
Okay, so that takes care of the making standard errors as small as possible by making the sample as big as possible. As a practical matter, the strategy that you're more likely to be able to draw upon is to try to reduce residual variance and decrease standard errors that way. So if you look at either Gordon or Woolrich, the standard error is essentially a function of the residual error, residual sum of squares. It's actually the root mean squared error, which is root is square root, mean is average, and then the squared error is just the error sum of squares. But it's that divided by essentially our sum of xi minus x bar squared. The square root of that, that's the variance of x. So the action item here is this residual error, and you want to make it as small as possible. Residual error means 1 minus the r square. So make small, in essence, means make r square as large as possible. All right, so not everything is fair game to do this. You can think of, suppose you've got your x variable of interest. This is your treatment, or other x variable of interest. So the key distinction is between what comes before x which are termed exogenous predictors, and what comes after x, which are endogenous predictors. You can think of exogenous as causally prior to X, and endogenous causally subsequent to X. And in this particular case, if you want to make the R square as large as possible and include additional variables to do that, any exogenous variable is fair game for that. Demographic, unchanging demographic characteristics, birth weight, child gender, parental background, all those things are usually causally prior to an X variable of interest. And they're all fair game. And you really want, for this purpose, I mean, you want these variables to reduce bias in your coefficient. But in this case, we're trying to make standard errors as small as possible. And to do that, we're trying to see if we've got exogenous variables we can put in that are highly correlated with the dependent variable, so we get a boost to our R squared.
Greg,
Yeah.
could you explain why being prior to X is exogenous and what it means to be prior to X?
That's a good question. That's a philosophical question, actually. You know, in some cases, it's temporally prior to X. Things that happen in time before X comes along. You know, let's say you've got some language program, dual language program that you put in first grade, and do, let's say, random assignment. You might have a correlational study where some kids go into that and some kids don't. But that all happens in first grade, right? So anything prior to first grade, kindergarten test scores, family background, anything like that can be thought of as exogenous. All right. Endogenous means potentially influenced in a causal way by X, right? So sometimes you want endogenous variables as mediators. That's what mediation is all about, right? If you've got X affecting Y, and you've got some mediator, Z, and you want to know the extent to which the effect of X on Y operates through Z, that's a mediational analysis. And the fact that Z is affected in a causal way by X means that it's endogenous, you know, which is great for mediational analysis, but it's not going to work here because it's an endogenous variable. You know, I was talking to, I was reviewing a paper that was looking at the effect of early childcare quality on age 15 outcomes. And it was someone in our school who did it, you might imagine, Deborah Vandell, with her colleagues. And you know, it's a very important question. To what extent does very early childcare quality affect outcomes for kids years later? And it was a nice analysis, except there was a version of it where they added in a whole bunch of 7th and 8th grade and 9th grade stuff it was termed soak up variance. All right, and soaking up variance is exactly what making the R square as large as possible amounts to, right? But they were putting in all these endogenous variables. And in effect, you know, if childcare quality was affecting age 15 achievement, let's say, by affecting 5th grade or 6th grade achievement, and you put this into soak up variance, well, you're likely to get a smaller than true estimated total effect of childcare quality on the outcome because you've included 5th grade test scores in here, right? It's a mediator. You want the total effect. You don't want what's left over after you include these mediators. Beware of soaking up variance with endogenous variables. Only use exogenous variables for that. Okay, so let's see if that works. We've got another example here with the data set from the class, and pause things and I'll set this up.
Okay.
Okay. So here we're going to illustrate the value of adding in a covariate that's highly correlated with the dependent variable. In other words, reduces the error sum of squares. So let's take our first regression. We'll repeat it here. 5th grade test scores on whether female, that standard error was 0.02. That's what we had before. Let's add in a variable in the data set that's strongly correlated with that 5th grade test score in order to explain 5th grade test scores. Absorb variance, explain variance, all those things mean the same thing. So here, Z-read4 is 1st grade test scores. And now we have a standard error on whether female of 0.015. So in other words, it's reduced from 0.2 to 0.015, which is a nice substantial increase.
You mean decrease?
I do mean decrease.
Okay.
Thank you. Okay, so we want it to be as small as possible. And we get, okay, so why don't you pause it for a second?
You're good.
All right. Oh, sorry for the little pause here. I was confused because the standard error fell from 0.02 down to 0.015, and yet the T ratio, how significant whether female was, dropped from 6.3 to 1.74. But if you look more completely, the coefficient dropped a lot too. So without controlling for their 1st grade test score differences, females have reading scores in 5th grade that are about 0.13 standard deviation higher. But once you control for the fact that their 1st grade test scores were higher, then you get a much lower coefficient. So that's why the T ratio is lower. But as I told you, only look at the standard error, and then I ignored my advice. So always always follow what I say and not what I do. But you can see why does the standard error fall? Well, how successful were we in increasing the R-square when we added in 1st grade test score? Well, if we just had whether female predicting 5th grade test score, the standard error was very small, 0.004. When we add in the 1st grade reading test score, now we've got a R-square of 0.45. So that's a big increase. Error sum of squares, residual sum of squares was 8,402. That's dropped to 4,570. So everything is consistent here. We've successfully reduced the standard error on the whether female variable by about a quarter. And we did that by adding in a predictor, a pretty highly correlated predictor, right? It's about 0.7 something correlation. So it's kind of hard to drive this down. But in this case, we could, because 1st and 5th grade test scores are pretty highly correlated. We boosted the R-square, we reduced the residual variance, and we reduced the standard error. Okay, so why don't you pause again?
Mm-hmm.
Okay, so Paul wonders whether everyone understands what a residual sum of squares is. And you're to be forgiven if you don't, because there are at least 4 ways to talk about it, and they all mean the same thing, or almost the same thing. Residual sum of squares, error sum of squares, sum of squared residuals, and sum of squared errors. All right, Gordon uses sum of squared errors, Wooldridge uses sum of squared residuals, and others will use these other terms. But they all basically mean the same thing. Remember that when we fit a line, we're using this least squared criterion. And if you think first of total sum of squares, which is probably talked about in 4 different ways also. That's before you even run a regression. You know, what's your best estimate if you only know y and x? The naive estimate, not considering the fact that y may systematically vary with x, is just to find the mean of y and try to predict all these points based on y mean. All right, so how well do you do if you do that? Well, for this first observation, with this value of x, you're off by this amount in the negative direction. Here you're off by this amount in the positive direction, this amount in a positive direction. So you can do this for all the observations. And if you take these distances and square them, right, it turns out the mathematics of squaring these distances is easier than just the distances themselves. For every point, find how far it is from this naive y bar, square those, sum them up, and that gives you the total sum of squares. That's what you're trying to explain. All right, so in a regression, you've got the possibility, let's say a linear regression, that there's a linear relationship between y and x. And if this indeed is the scatter here, then it looks like there is definitely a relationship between y and x. A positive one. So let's apply our formula for beta that we talked about in the first day, and get a best fitting line y equals b1x. So now let's go through and repeat the exercise to get and explain sum of squares. And again, there are different terms for this. But now we go through this exercise of looking at distances. And we see that the distances, for the most part, are quite a bit shorter, because we're allowed to account for this linear upward relationship between y and x. So you're going to get squared distances that are smaller. So the explained sum of squares is going to be a substantial number, not as big as the total sum of squares, because you still have some unexplained distances here. But if you take the total sum of squares minus the explained sum of squares, then you get the error sum of squares, the residual sum of squares. No sum of squared residuals, no sum of squared errors, right? It all means the same thing. So we've given it our best shot in this regression by estimating the best fitting linear relationship. We still have some ways to go. but the inner sum of squares is definitely smaller than the total sum of squares. And the more, it's hard to imagine this in multi-dimensions, but if you can add in more predictors, add additional dimensions that are highly correlated with y, then the kind of multivariate distance from the best fitting line gets smaller and smaller, right? So if you think about the formula for the standard error that I just erased, the numerator is essentially the error sum of squares, right? So you want to make that as small as possible, and additional predictors do that in the same way that this one predictor reduced our total sum of squares quite a bit. Okay, so if you have lingering questions about that, ask Paul or ask me about that. Okay, so continuing on with our fun with standard error section. A third use is to use the standard errors to diagnose multicollinearity problems. So multicollinearity can arise if you have many highly correlated predictors. And remember, we said more predictors is usually good because it gives you, it reduces limited variable bias. The variables aren't omitted, they're included. But you don't want to have so many that are so highly correlated that standard errors start to blow up. And if you've got, again, our 0.20, let's say that you were starting out with an effect size of 0.20 with standard error 0.05, if you start adding predictors to that equation, this isn't such a good example because if it's a randomly assigned treatment, you're not going to get variables that are correlated with treatment assignment. But in real life, you've often got a variable that is correlated with other predictors. And if you add in a bunch of these correlated predictors, you don't change the estimate, but let's say you, the example was triple the size of the standard error. You can triple the size of the standard error by having a smaller sample size, but you can also triple or quadruple or by 10 times increase in the standard error because you're putting in so many other correlated predictors. So one nice guide to whether or not multicollinearity is a problem is what's happening to your standard errors. All right, and if they're increasing by a lot, then you start to worry. There are other more sophisticated diagnostic tools for multicollinearity. There's a variance inflation factor, VIF, that Stephen can give you, but this is the quick and dirty way. You should always be kind of monitoring what happens to your standard errors as you estimate models that have more and more of these independent variables. So let's pause for a moment. Okay, so now I'm sharing my screen. This is just the basic first table from Fryer and Levitt. And as you can see, well, here's the difference between each of these categories, kids in each of these categories, and the omitted category, which is white. But here we're concentrating on the standard errors. So we've got a 0.029 standard error for the difference, estimated difference between blacks and whites, a 0.028 standard error for Hispanics versus whites. And the question in this case is, to what extent do these standard errors blow up when you add a bunch of correlated variables, right? So they have a lot of background variables: age, birth weight, child gender. Those wouldn't be expected to be very correlated with Black and Hispanic. SES measures, there's a measure, an explicit measure of socioeconomic status, mother receives WIC benefits, mother teenager at birth. All these kind of background variables might be correlated with being in the Black or Hispanic or Asian or other race categories, and throwing them all in. And if you read the article, they actually start out with 100 of these variables, and they trim them down and find that this smaller set produces essentially the same results. When you add these in, this is fall of kindergarten test scores. These are math test scores, I think. So the coefficient falls a lot, 0.40 to 0.13. Goes from negative to positive, which in this case means that once you control for all of these differences between Black and white kids, Black kids actually have an advantage in terms of kindergarten test scores of 0.13 standard deviations. But the point here is to look at what happens to the standard errors when you add in all this stuff. Do they double? Do they triple? Well, they go from 0.029 to 0.032. So they don't change very much at all. And that's pretty much the same for all these variables. So, you know, I've heard people worry about throwing in, you know, all these background variables for fear of multicollinearity. But I can guarantee if the standard error isn't budging, which it's not by very much at all, 0.029 to 0.30, more sophisticated diagnostic tools for whether there's multicollinearity problems are going to show it's not a problem. So keeping an eye on these standard errors as you add variables into your model is a good thing. You can see that in the class data set as well. All right, so now we're starting to get something that doesn't make much conceptual sense. We had 5th grade test scores as a function of 1st grade test scores. Let's add in kindergarten test scores as a pretty highly correlated variable. Remember the initial correlation matrix up at the top here. 1st grade test scores and kindergarten test scores are correlated 0.76, which is pretty high. So you might think that adding in kindergarten test scores to 1st grade test scores and child gender as it predicts 5th grade test scores might cause a lot of multicollinearity problems. But in fact, you start out with a standard error on the 1st grade test score of 0.0076. And now when you add in kindergarten test scores, you go from 0.0076 to 0.1175. All right, so roughly a 50% increase in standard errors. It's not zero, but it's not that worrisome because it could be a lot worse. So oftentimes the kind of increases that you get are in the 10%, 20% range increases the standard errors. 50%, if it's a theoretically interesting control variable, you still have a lot of precision on your estimate of 1st grade reading scores, even though the standard error is 0.12 instead of 0.008. So it's this balance between wanting potentially to control for these correlated variables to reduce omitted variable bias, versus losing precision on your estimation because the standard errors are blowing up. So, by and large, it's not as much of a problem as most people think, but it's something that you should keep an eye out for as you do your work. Okay, let's stop.